Okay, good morning, everybody. So for our first talk, we have Jochen Heinloth, who will speak on canonical and semi-stable reduction for Hodge bundles and related moduli.
Thank you very much. Yeah, thank you very much also to the organizers for the invitation to this very nice place. And thanks for the previous speakers too, throwing a lot of analysis at me. So I actually enjoy this, although yes. But this also causes a kind of a start with an apology that I usually try to avoid, that I will probably speak in a different language, but just stop me, right? So if you get lost, if you cannot translate it into your favorite language anymore, let me know. Okay, and so the other apology that I have to put in the beginning, so I will state a theorem at some point, but since I last gave the talk, I got confused about one point that doesn't matter for the applications I have in mind, but there's a subtlety that I will kind of hide. Okay, so what's the aim of the problem? So the aim, so we saw in many of these moduli spaces that we started with, it's the old theme. You have your moduli space. You've found some semi-stable part that is too large, so you cut down some semi-stable part. And now, for reasons that I will disclose, I'm interested in in find Adenauer-Zimmer. Or Kempfness, if you prefer. Oh, yes, so find Adenauer-Zimmer or Kempfness stratifications of the complement. And then Halpern-Leitzner now introduced this. He calls these theta stratifications for reasons that I will recall. So these are names for the same thing. And so why am I interested in this? So there's essentially two distinct. So the first reason why I started this is in a joint project with Oscar. So one thing is, so variation in if you have a modular problem where you can vary your stability condition, then what usually happens is the following, that so you might have two versions of semi-stable objects. So, and if you do that are related by what people call wall crossing, and if what this wall crossing, how you can compute how this moduli spaces changes is from the point of the moduli problem. It usually looks like as follows, that, well, you want to go to the positive or the negative side, I don't know. So that this usually looks like you do the following: you take your semi-stable part, you add a union of some Adenauer-Zimmer strata, and then remove a few Adenauer-Zimmer strata for the other thing. And so the toy picture that you probably have in mind, hopefully. The toy picture I always have in mind is if I take just the two-dimensional affine space with the anti-diagonal action, there are these, you could either, if you want to have a stability condition for which semi-stable is equal to stable, you can remove either this line or this line, and this is what happens. So you add the missing line. So this is the Harder-Nurseman stratum you add, and then you subtract the other to go to the other side. And in many cases, this is an honest local picture if you interpret this two-dimensional picture as an n plus m dimensional picture. Okay, so that's how this happens. And so even if I'm just interested in semi-stable objects, I might still want to know what the geometry of the unstable strata are. And this is not all unstable strata, but those that are pretty close to my semi-stable locus. Okay, so this is how my problem appeared for me for this talk. We wanted to variation of stability and did some computations, and then Oscar said, well, you can probably prove easily that there exist these Harder-Nurseman specifications. So that was my task. Good. Okay, so that's yes, that's what's, and the other thing that sort of when I started writing this, I got an email on these questions of things that are kind of known in some cases, some generality, and then people want to have a reference, and then you start looking and you can't find one. There's a sort of so properness properties, so compactness properties. So this. So both compactness of moduli spaces or like properness of the Hitchin morphism from the semi-stable locus. And there's a general, so from my perspective, how this is, I mean, in algebraic geometry, this is usually done by first proving a statement on the large moduli space, which is not so hard, that you can always extend families, but then you don't know whether you can extend semi-stable families to semi-stable families. But in this joint work with Dan Halper and Leinster, Gerard Alper, we proved a rather general semi-stable reduction theorem that allows you to do this whenever you can have a theta stratification. So for both of these things, the issue is the same. You have to find these canonical reductions. And I should also say that there's a recent article. So there's work of Dan Halper and Leinster. And Andres Fernandez Herrero. And this, they call this moduli of gauged maps, but I don't. I don't know how they came up with this name, but so that does this in certain situations, but my main examples are unfortunately not covered by this. It's a bit of a pity. Okay, so I had to look back somehow. So what are the settings I'm interested in? So the settings for which so what I want to do is just in this talk, well, first tell you a bit about the settings that I'm interested in, and then tell you how if I interpret Behren's canonical reduction argument in this kind of language, it becomes became simpler to me. And I wanted to share this, and it applies in a kind of general context. Okay, so the settings I'm interested in is, okay, so sorry, I'm here. So I fixed a smooth projective curve. And I would like to have a setting that includes the list of the following things. So of course, I want to have G bundled. G is some reductive group. So I want to include, because I'm here at this conference, I want to have Higgs bundles. I also want to include, so maybe I can put this here because in this conference also for real groups. And I also want to have this thing to apply for the C star fixed points. And this came from this email request, kind of, I would also like to include parabolic versions. And it would, for me, it would be nice to have one setup that includes all of these, so that I don't have to do this over and over again. And I want to, yes, so I want to explain, well, the for me kind of natural framework in which these would all fit. And then we see. So how do I want to say this? So if I write bun-G, I think of the moduli of G bundles on the curve, all of them. For me, it's an algebraic stack, but you think in the language that you like. And sort of since it's here, but this. This had been written like this as maps from the curve into the classifying space. That's by definition what G bundles are. And it took a while for algebraic geometers to make sense of this. And one thing is, well, maybe here I don't know. So for me, BG is the algebraic stack that you obtain by taking a trivial action on a point and taking this quotient. And how do you think of maps into this? Well, what this is, if you like stacks, then you like this object. If you don't like stacks, then you probably don't, but you still, the only thing you need to know is what maps into this thing are. And that's not hard to say, because maps into a quotient are just maps into the locally maps on top, and then you allow for patching that uses the structure group. So that's why this is G bundles, you see immediately, because locally that maps to a point. So locally this is trivial G bundles, and then they are obtained, then patching is done by gluing functions. So that's kind of obvious. So the good thing, yeah, so maybe the next thing to look at is probably bundles with sections. So Higgs bundles are G bundles together with a section in an associated bundle. So let's first try to do this. So if I now take a representation of my group, then I would write it, and if I take E, a G bundle, then I will write EV for the associated vector bundle. And I would like to have the moduli problem that takes a G bundle on C together with a section of the associated vector bundle. And how would you write this in this form? If you are one of the people who just nodded when I explained how you think about this, then you hopefully will nod again. What maps into this? Well, locally it's giving you a vector here, and then you then you patch by taking G bundles, which is exactly what you do. Locally, you take a section in V, and then you glue your objects by applying G. So this is this thing. So now this is this annoying thing. So this is perfectly covered by this article of Enhalber, Leinster, and Andres. Now the problem is that for Higgs bundles, you would like to put, you don't want to have this. You want to take the Lie algebra, you want to take the adjoint or the co-adjoint bundle and tensor with the canonical bundle of your curve. And this tensor is absent from this. That's annoying. But Go Chao explained how to get this in back. So Go explained how to put this in. And he said the following, well, if I look at this again, there, if I have a representation of a group, there's also the scaling action on the vector space that also acts there, and I can just take the scaling action. Usually, if at some point I write GM, then think C star. I try to force myself to write C star for today. So if I look at this, well, what's this? Then, so this has a map to and the classifying space of C star is just line bundle. So what will this be? This will be pairs of a G bundle, a line bundle. So this is the C star torso that you see here. And then if you think about this, it's locally sections in V that where you allow the gluing to be changed by G and C star. And so now you got your section N. In here. That's not hard. That's still not what we want to have because we want to fix our line bundle. And that's actually important because, yes, because the exchange morphism, this is obtained from taking characteristic polynomials. And if I also take the C star action quotient, I will contract them all to a point. So if I do it in this global family, I will contract, there will be no base anymore. So the natural map will be to a point, and that's not what if I want to prove properness of your vibration, this won't work. So I will have to do this, but this I just do by, so if I take my canonical bundle, I just define this to be, okay, it will not matter. So I will just define this to be the fiber product of what we have. I will define this to be the fiber product of so this has a map to pick. And then you just take the point that's given by your favorite line bundle. And you take the fiber product. And that's the kind of object that I would like to look at. So that now I have sort of also, now I have allowed to fix this line bundle, and this is the moduli space I want to look. Okay, we have time. So I want to at least mention there's a parabolic, so there's a variant with parabolic structure. This is big. So it takes okay, now this classical object now has too many names. That one is definitely too fancy, but it's, yeah, okay, so there's variance with parabolic structure. And what you do is, well, for my favorite way of doing this is to replace G by the automorphism group of a bundle with your parabolic structure. So, and these are called parahoric group schemes. So by so a family of group over C. So this allows to have bungee to be G bundles with parabolic structure. And then you can try to run the same thing, and your representation will then become a vector bundle on C together with the representation of G into. A question? So this is so it sends the unique object here to the canonical line bundle here. Right, so this is a point. So this is the fiber product. So this is defined to be the fiber product. So objects in here are objects in here together with an isomorphism of the line with an identification of this line bundle with your fixed line bundle omega. And it could be any line bundle here at this point. I choose omega because this is what I'm interested in for Higgs bundles, and because I don't have a good second letter for line bundles, and I will have other line bundles, so the L's. So omega can be any line bundle, but that's what I think of. Okay, and then you can do the same thing. Okay, so what's next? So next thing is I have to maybe you all know stability, but we all think of stability in different ways. I presume. Yes. Yeah, so you have all thing in then you can do this thing right away, and then if I didn't confuse myself too much, then in this situation you can sort of put the omega c into the v, and you have the twisting right away. But so stability. So stability is what Dan would call theta stability. So this is modeled on GIT. So for me, it depends on the choice of a line bundle, or rather on the modular problem, or rather the only thing that matters is the first Chern class. So the only thing that matters is the first Chern class, so you will probably prefer to think of it as some form. Okay, and how, what are the line bundles here, and how does this, maybe, I don't know, will I have to recall this? So, so the line bundles, yeah, so I should say that all of these spaces, they have forgetful maps to bun-G, and I will only give you line bundles on this bun-G, and I will consider them sometimes on these other spaces just by pullback. I will not keep this in the notation. So on bun-G, for most of the time, there's only one choice that I'm slightly lying, but okay. So there's the determinant line bundle, which is, well, I don't know. You have to ask if you. So I hope you have seen it. If not, I mean, what do you do? What does the line bundle on a moduli problem mean? So for every point, I have to give you a line, and that's the line. So how do I, if you give me a principal bundle E, how do I make a one-dimensional vector space out of it? Well, I take the cohomology of the adjoint bundle. I mean, some associated vector bundle. The adjoint bundle is the only natural choice I can think of. And I take the determinant of this cohomology vector space, and I get a one-dimensional vector space. And for some reason, I have to take the dual to make this positive. So that's one choice. But then, and this happens a lot in these other examples for these real Higgs bundles and for these C-star fixed points, if my group is not semi-simple, I could take a character. I could take a character of my group. And this, the character, so this gives me a line bundle on BG. And this again, you can pull back, for example, choosing a point on your curve. You can pull this back to make it into a line bundle on. And this is usually where people take their stability parameters in. So you take L, so this will be L det, and there was L chi, or some chi. Okay. Yeah, so what does this do? Maybe I should say, so for Bungie, it's a really bad idea to put any of these characters chi, because if you compute what semi-stability means, it's this, whenever you take a non-trivial chi, everybody will get unstable. So it's not a good choice to put. But what does this actually do? Well, in this case of your representation, so what does this do? This mixes stability for G bundles and the GAT stability on V mod G. So if you have a group acting on an affine space, I mean, you can take the affine GAT quotient, or you take the GAT quotient with respect to some linearization, with respect to some character, and this is sometimes better. So why is this a good idea? Yeah, maybe in the examples. Yeah. So one example that came up in this work with Oscar is the following. You take and sorry, I have to think how to say this without making Oscar upset. So you start with a group G. This will not be the G, so I should call this with a larger group G, and you take a one parameter subgroup, so a co-corrector. Then you take your G0 to be the centralizer. So it's just some Levy subgroup. This is a Levy subgroup of G. And then this also, so this happened. So if you want to look at these star fixed points on Higgs moduli spaces, you will find the following. So this also gives you a grading of the Lie algebra. Where this is the weight I part of the lambda of the star action. And what happens for these 6 points is that you actually look at this mapping space. Again, twisted. Or in the degree 1 part of this thing. So you took your Levy subgroup, and this is the G1. And the quotient group is G0. Yeah, so I called it G0. Yeah. I called this G twiddle. Was, yeah, okay, this was not. Okay, good, yes. Sorry, yeah, anyway, good. So this thing is, and this is actually a funny thing, is that G, which is this G0, acting on G, yeah, but it's also good to call it G0 because it's Lie algebra is the zero weight. So, good. Anyway, so this acts with a dense orbit. And finitely many orbits. But this is sort of why variation of stability is, so you think, well, okay, this is ridiculous. But if I take a GRT quotient, I will always get a point. Or an empty set, even worse. But if you play GRT stability with this thing, then you will force your section to generically lie in the open orbit. And if this open orbit is unstable, and if you play with stability a bit more, then you will force your section to entirely lie in the open orbit. And this gives you a simpler description of this mapping space, because now you're just looking at essentially a classifying space into the stabilizer of this open orbit. And so this is this is why moduli spaces in this way might become more accessible. If you vary stability, even in these very silly situations, in the end, you only consider maps into a very restricted class of objects. And that's actually what happened when long ago with Oscar, we did this article on moduli of chains. So it wasn't formulated in this way, but this is how I would explain it now. Okay. Yes? Right, it's varying this character. And so if I would go into this parabolic situation, there would also be more line bundles here, and I could also vary those. Okay. Do I have to, yeah, maybe I remove the parabolic structure. So what's stability? I write, yeah, okay. And maybe I should call it, so this L stability. So M will be any of these moduli spaces. And L will be this line bundle. So how do you find stability? And so there's the GRT version for algebraic, for these moduli problems. And I just formulate them, and then you throw tomatoes or get bored. I don't know, something in between. So if you take a point X, the analog of the Hilbert-Mumford criterion becomes the following. It looks abstract, and then I tell you. So it says that for all maps from what he calls theta, that map the point 1 to X, on this X twiddle, I can take this map X twiddle, pull it back, pull the line bundle back, take the zero fiber. The zero fiber is a line bundle on point mod C star. So this, I can take the weight. So it's just a line with a C star action. And I want this weight, so it's semi-stable. If this weight is always bigger or equal to 0. So some parsing of this. First, a word of caution. When it comes to these weights, there's a sign convention embedded. It has to do with, I think of a line bundle as its sheaf of sections or as the geometric object. And so there's a sign convention, and these sign conventions are not uniform in the literature. And the worst thing is that when I worked with Dan Harper and Leinster, I think we convinced each other that our sign conventions was the better one. And so we switched. And so that's kind of the most unfortunate outcome. Anyway, so what this means is just, well, whatever this, so what does this mean? This is just a C star equivalent line bundle on the affine line. And this condition just means this has invariant sections. Non-trivial invariant sections. So if I think of this algebraically, a line bundle on the affine line is a module for the ring of functions, a free rank 1 module for the polynomial ring as a generator. This generator, well, there's a unique non-vanishing section. This generator has some weight. All other weights that appear applied by taking powers of the coordinate multiplied with this thing. And so if I have weight positive, the weight of the coordinate is negative, I can make this 0. If the weight was negative, x to the I times this thing will be even more negative, so there's no invariant section. So whatever the normalization for your sign is, this condition just means the pullback of this line bundle has non-zero vanishing section, invariant sections. Good. So now, probably should also recall, I don't know, yeah, maybe I should recall quickly. So this looks pretty abstract, but it is just filtrations on bundles. So this is the same as weighted filtrations on G bundles compatible with the section. So what do I mean by this? So the basic computation is the following. I should probably say co-character. So okay, let's try to unravel this. So if I take maps from point mod C star, so that's just BC star to BG, well, the trivial bundle gets mapped somewhere, so you get a map from C star into the automorphisms of the trivial bundle. So you get a map from C star into G, and this is well defined up to conjugation. And that's actually all there is. And then if you start out with this co-character and try to lift this, to integrate this out for the direction that your coordinate is flowing in, you will find that you will get a bundle with a reduction to the so every bundle for the levy has a canonical reduction to the, well, it's a bundle for the levy, so I can consider it as a G bundle. And in between, it's a bundle for, so this is the parabolic for the line bundle. So this is the the points that are flow to the centralizer when I let lambda go to 0. And if you compute this reduction of the G bundle to the parabolic lifts canonically along this flow line that you have in, and then you check that this is an equivalent. Okay, there's many ways to say this. Oh, it's easy to explain for GLN, but I don't want to. Maybe you just believe this. So there's one thing that and then if you apply this machinery, if you want to have maps from theta, from C modulo C star, into your mapping, that's why this is kind of great. Into bungee, you can just flip the maps around. So it's maps from the product into BG. So this is, you can turn. So this is then P lambda bundles. And that's how you see that this really is just taking a G bundle with a reduction to a structure group to a parabolic. There's one kind of thing that I should mention, and that's kind of both good and bad. Reductions to parabolics I like, and I know that there's finitely many conjugacy classes of parabolics, because I also choose this co-character in the center of the levy. I put countably many copies of the same thing, although this is a finite object. I mean, I think of the parabolics as being finite objects. So this is kind of, sometimes it's a bit of a mess that you put this additional weights. And this is the same thing that you see in these DIT computations. At first you learn that this is about filtrations of vector bundles. And then if you look in more details, actually people say that the numbering of your filtrations actually matters. And that's weighted filtrations. And that's the same thing, difference between fixing the parabolic and fixing the numbering of your filtration. Good, so that's this. More questions on this? Maybe I put this theorem in quotes now. So it works for these examples that I have put here, but for a general representation, I got confused. So I have to be a bit careful. So maybe I call it claim, because I haven't written it carefully. Maybe I just call it claim for today. Hopefully I get unconfused by the weekend. So if for any positive line bundle L on bungee, I will tell you what this positive means. I take any of these line bundles L, and I will have to give you the positivity condition in a second. And X inside my mapping space twisted mapping space. There exists a unique reduction I called these reductions. I said this was maps from this thing is called theta. Such that the weight of X tilde. So I would like to, now I have to check my conventions. So for semi-stability, I ask this weight to be positive. If it's unstable, this will be negative, this maximum. And sort of lambda is unique up to scaling. Right. So that's this. So I should say, so the problem, so why do I have to have this normalization here? So usually you think of these canonical destabilizing things as having a maximal degree. And here comes this co-character in that, well, this, whenever you give me such a reduction, I can just multiply lambda by any number. I get another reduction that will scale the weight by this scaling of lambda. If I place lambda by 2 lambda, you look confused. So these parabolics, p lambda, they don't change if I replace lambda by 2 lambda. So giving me a map to this thing or to 2 lambda is the same thing. So I can always replace this x tilde by 1, where I replace lambda by 2 lambda. This will multiply the weight by 2. And so that's why I have to renormalize. And where sort of this norm of lambda is an invariant. So the norm is an invariant inner product norm on the co-characters of G. Or well, more classically, you take the Veil invariant inner form on T. Okay. So that's, maybe I should say classically. I plan something to say. Yes, but this is only determined up to conjugacy. So. Yeah, so this was always only the parabolic is canonical, the lambda is not quite, but there's the natural ray, and that's usually not mentioned in, in the classical thing. Maybe I should say this. I'm sorry, I'm probably spending too much time on old stuff. Doesn't make sense otherwise to me. So classically, for vector bundles, you have this canonical. You take Harder-Nernst-Riemann filtrations. Where you take the degrees to be maximal, so the slopes to be decreasing, and then you I had noted something how I wanted to write this. Yes. So the point is, if you have a bundle, so suppose for simplicity of this talk that this is a full flag. Then if you take, and lambda is a co-character, the Borel giving this where this is a reduction, then you have choices of lambda, and what comes out is that this is the degree paired with lambda, and this is sort of the killing pairing. So what is the degree? So you have this degree. This is a function from characters of the torus to the integers that takes your vector bundle Yeah, you take the associated graded and multiply them together according to your character. And then sort of this is the thing that often you see in these things, that you take the degrees to be maximal. And here you see sort of, if you want so this degree, I can view this, I mean, it's a linear function from so it's itself a co-character. So it's a linear map from characters to Z. So this is itself a co-character. So, and this is the pairing between co-characters. And if you compute what this weight is, which is not hard in this case, you find this. And this tells you why this lambda never appears in the classical part, because if you want to multiply this and this degree is positive on all of the, I mean, if the slopes are decreasing, then the maximal lambda to choose is the degree, or rather minus the degree, depending on the sign. So that's why this is hidden. Okay. Yes. I wanted to do I wanted to explain what Behrend's argument for this was. So Behrend proved this for BG, and I wanted to recall this in this language. Okay. More questions? And if I understand this correctly, then to me, this starts with a pretty silly. So the main computational input in this proof from Behrend's argument is for me the following. So you take the stupid case, you start with the group to be SL2. Let's prove this uniqueness for SL2. You know that, so if I have a vector bundle, the rank 2 bundle, and suppose you have a destabilizing subbundle. So meaning that this degree here is bigger than the slope of this. So this degree is 0, so that this degree is positive. Then this thing is unique for a very stupid reason. Because if you take any other bundle, well, it's a different line bundle, so it injects here. But this degree is negative, so this degree has to be negative. Even worse. So what you get from this thing is very stupid, that this is smaller than the degree of Q, and the degree of this L is smaller than the degree of the quotient. Right? They are different, so they're distinct at the generic point. So generically, this maps to non-trivially, so it's an injection of line bundle. And so what you get is that the degree of L minus the degree of Q is smaller than minus the degree of L prime minus degree of Q prime. So the uniqueness is immediate from here, because it just says if you have one that is positive, then all the others have to be negative. So if you found one destabilizing reduction, it's the only one there is. And this gives you a very strong convexity property here, that you can not only determine this weight for the reduction you found, but you even can estimate it against minus the degree of the other. That causes some confusing signs, but this is sort of so gives a strong convexity. And so how does the C use this? So this very silly case. Oh, it's unreadable, I see. Yes. This gives a strong convexity property. So this silly computation will give a very strong convexity property for this weight function. Isn't quite, oh, my time's, I thought I had 5 minutes. 5:55. Yeah. Okay, let's make this quick. So that's the only blackboard I will use. And then I'm, no. Here notice said the following. Okay, suppose you give me 2 reductions. So then you know that whenever, so this is a choice of 2 parabolics in G, and any 2 parabolics share a common torus. If you unravel this, this means that any 2 reductions of a G bundle E to parabolics can be obtained from a generic reduction from a common to a torus, to a maximal torus. So in the vector bundle case, what you say is just please choose a basis of your vector bundle generically, such that both flags are obtained from putting some of the basis vectors together. So a general reduction to a torus defines you a generic reduction to all of the parabolics contained in it, and this automatically extends to the whole curve by properness. He does this. And so now look at the weight function. So that's the degree, but so now I take the weight function. Z maybe. That takes, whenever you take a co-character, you put this to the weight of the associated reduction to P lambda. Right, so your co-character defines your parabolic. This parabolic defines you this reduction, so it defines you this thing. And what you figure out is that this is locally, so this is linear, when it's piecewise linear. On the Weyl chambers. And piecewise linear and linear continuous. So if you extend all of this to the reals, linear on Weyl chambers. Because in a given Weyl chamber, the reduction that you get here is always the same. It's always the same Borel. And sort of then you compute what is this weight function for these 2. If you have 2 Weyl chambers and they match in a common phase, this means you just flip one root. And so this computation tells you how the weight changes. Flipping one root is an SL2 computation. This gives you a strong convexity. So this thing gives you a convexity property here. And this forces a unique maximum. Now you think, okay, but if I now do, in my last minute, so if I now do Higgs bundles, I cannot run this argument because not all reductions will be allowed. Only those that are compatible with the Higgs field. Damn it. Then you look at Kempf's article on the canonical instability flag. And he says, well, this uniqueness of the maximum still holds if you restrict this to a cone that's cut out by rational hyperplanes. And this is what the Higgs bundle does. It's just the weights in which you, I mean, you have your Higgs field, you have your reduction to a torus, So you take the weight decomposition of your Lie algebra and see in which weight parts does your Higgs field actually appear. And the lambdas are allowed where this weight is positive. This puts a linear restriction just as in Kemp's uniqueness argument, and so you apply the same argument, you get the uniqueness result. Okay, I brushed under the rug the existence of a maximum, but that's the thing I got. Oh, yeah, good. Thank you.
Okay, thank you very much. Are there any questions?
Is this setup working in the situation where you have a G bundle, let's say, and now the section is not associated to a representation into a vector space, but actually just a Higgs field that is nonlinear. So it's, you have G acting on another variety.
So then, and in this article, they take this setup without the twisting, and you're allowed to map into any X mod G, either projective or affine. In that article. They don't allow for the twisting though. And that's sort of annoying for applications. I think if you can make this work for a general representation, so for the Higgs bundles and this G0, this point that I brushed under the rug badly is okay. If you can prove this in general, I think that, well, if you have a algebraic G action on an affine variety, you can embed this into a representation. And this, so it's cut out by something closed. So once you can do this for the vector spaces, you probably also get a result for affine motions. But okay, so they do this in this general thing, but without the twisting. But sort of if you just take maps into something without twisting, then their article does this.
Well, it's not clear what twisting means in that situation, right?
Yes.
Yeah, okay.
No, well, it is, to me, it is clear because of the other setup, right? You take a family of spaces over your curve and take sections. That's what the twisting does. So that's how you could form a, I mean, you could take maps into one space, or that's the same as sections of the product. And twisting means you take something that's a fiber bundle of this.
Other questions? Yeah.
Hello. So can you say some extra brief words about these codes that you just mentioned, but about what you just said about the compatibility with the Higgs field?
Yes. So then this. So choose a local, so generically, you have your Higgs field. So generically, this phi is an element in the Lie algebra. And now this Lie algebra becomes graded, so you can write this phi into weight coordinates. You take the decomposition into weight spaces for D, and then this phi being allowed means that that phi D is non-zero, implies that D is bigger or equal to 0. That's the compatibility with the Higgs field. And that's the hyperplanes that you have to. So it's this combinatorial structure. And so in general, this also tells you that the hyperplanes are not totally arbitrary, but they are given by things in the root lattice.
Any further questions? Okay, if not, let's, thank you. Organize, should we do 20 minutes or 15 minutes of break? 15? 20? Okay, well, anyway, so I guess we'll start again.